Hello everyone, I'm Luciano Oliveira, professor at Federal University of Bahia and head of iVision Lab. I'm here to present a work entitled Deep Speed Estimation from Synthetic and Monocular Data. Speed measurement is one of the main allies of traffic surveillance systems, mainly for their management and enforcement. Vehicle speed can be used to determine possible accidents, hazardous areas in rush hour, and wrong or unsafe driver behavior. Several countries use systems of speed control to enforce road speed limits with the goal of preventing traffic accidents. Systems for speed measurement can be split into two categories. Active, which measures the effect of signals transmitted to a vehicle passing on a highway, and passive, which comprises video systems whose analysis of consecutive video frames serve to track a vehicle and thereby measure its speed. For active systems such as radar, sensors that perform speed measurement are used to trigger a video camera to record plates of the vehicles. This active device emits a continuous radio signal wave, captures its reflection and calculates the speed. It works based on the analysis of the wave that was emitted. Another type of device commonly used is the inductive loop detector. This device uses sensors installed on highways called inductive loops. When a vehicle with a metallic body passes through an inductive loop, it causes a disturbance in its magnetic field. This disturbance is processed by software that can detect the time that the vehicle has spent from one inductive loop to the other. Such sensors are usually expensive and require extensive calibration and maintenance, besides having complex installation requirements. On the other hand, video-based systems have become popular due to the technological advances in cameras and computer devices. Additionally, the cost-effectiveness of these systems brings advantage over traditional ones. This way, it's possible to make speed measurement simpler and cheaper by using information extracted from video frames. Three steps are required to obtain the speed of a vehicle from a camera. Vehicle detection, where each vehicle passing the scene is located. Vehicle tracking, where the detected vehicle is tracked until it leaves the scene. And camera calibration, to find the parameters needed to transform the vehicle trajectory shift in pixels to some real-world unit. For speed measuring, it is necessary to obtain the time values, wherein a vehicle travels a route and the travel distance on the road plane. The time measurement is the trivial part to be computed. However, to get the distance, one needs to know the actual distance between 2 points on the road. For that, calibration is demanded. In this context, calibration methods can be manual or automatic. Manual calibration usually requires distance measurements on the road plane. Automatic calibration usually takes into account the mean vehicle dimensions. For each environment in which the estimation will be carried out, it's necessary to obtain some distance measurement on the road to be used as an input of calibration. The major limitation of current works is that for each environment, camera calibration is required to calculate speed in terms of actual measurement values, for example km per hour, rather than pixels per frame. Then, for each environment in which the estimation will be performed, it's necessary to obtain some distance reference on the road to be used as an input for calibration. Even automatic calibrations need some real measurement, which in this case is the assumption that all vehicles have roughly the same length. The vehicle's average dimension is used as a real-world reference to obtain a scale factor to compute the real vehicle speed. There are only two datasets of vehicle speed measurement publicly available. In our work, we used only synthetic data to build our speed measurement system without any real-world measurement, eliminated the use of calibration or manual input for this purpose. The use of the simulator when generating synthetic datasets allows for the construction of several scenarios that can reflect the real world by generating varied samples with variation in weather and light conditions, which can be difficult and costly to be captured in the real world. We validate our systems in the Louvizon's dataset, and we achieved competitive results by using only synthetic data. At first, we created a synthetic dataset using the Carla simulator. In this simulator, it's possible to obtain vehicle speed data along with its route. We used three scenarios to make the capture, two of which are of urban perimeters, where vehicles travel at low and medium speeds, and one of expressway, where vehicles travel at a faster speed. We applied five different weather conditions to obtain the data: clear noon, sunset, hard rain noon, wet cloud sunset, and wet sunset. We generated 32 videos ranging from 10 to 40 minutes, totaling 9 hours and 30 minutes of video approximately. From this dataset, we extracted a density optical flow. The average of the density optical flow is calculated and used as an input in a deep learning regressor. Our regressor is based on a VGG network that we have adapted for this purpose. Our synthetic dataset contains more than 12,000 of vehicles along with their corresponding speeds. In the simulator scenario, we demarcated a speed estimation region and placed a camera aimed at this region. Thus, there is a line defined when a vehicle enters and another line when the vehicle exits. The average vehicle speed between these two lines is recorded for each vehicle that passes through that region. The input video is captured by a single fixed overhead camera, positioned so as to view the rear of the vehicle in a single location for each synthetic scenario. This speed is obtained from the Carla simulator. We used faster RCNN to detect the vehicles and deep sort to track the vehicles located by our detector. The tracking systems allows to identify which vehicle bounding box from faster RCNN are part of a particular vehicle. From the moment the lower left point of the vehicle's bounding box passes the first line that marks the beginning of the measurement, the estimation of the density optical flow is performed. The estimation will last until the lower left point of the vehicle's bounding box passes the last line that marks the end of the measure. We extracted the optical flow information using a state-of-the-art neural network called the FlowNet2. After obtaining the motion data, we averaged the optical flow tracked within the speed measurement region. The result of this average will be used as an input to our deep learning regressor. Before reaching our regressor, we carried out some tests with ResNet variation. ResNet with 18 layers, ResNet with 34 layers, and ResNet with 50 layers. We realized that as we increase the number of the layer, our training goes to overfitting. Therefore, we chose to adapt a simple VGG16 convolution network for our proposal. We used the exponential linear unit as an activation function instead of the original ReLU in the convolution layers of the network. At the end of the convolutional layers, we added an adaptive average pooling before the fully connected layers. This allows our regressor to receive the optical flow average of vehicles tracked in different dimensions without having to resize them, avoiding losses. We used two fully connected layers with 496 neurons, and a layer with a single neuron, which is the estimated vehicle speed. Our network is trained in MSE between network output and vehicle speeds targets for 2000 epochs long. The other optimize is used for training. We used the Louvizon's data to validate our estimator. Louvizon et al. Estimated the speed of the vehicles by tracking their license plates using a KLT tracker. To find the speed in km per hour from pixel image, Louvizon and colleague uses a perspective rectification from a measurement performed on the road. The author reached an average error of minus 0.5 km per hour and a standard deviation of 1.36 km per hour. The maximal nominal error value found for speed across the raw dataset was between minus 4.68 km per hour and 6 km per hour. Our system uses a regressor that has been fully trained by gathering synthetic data. It managed to achieve a relative precision in our estimation, reaching an average error of minus 0.778 km per hour and a standard deviation of 2.64 km per hour, with a maximal nominal errors between minus 29.81 km per hour and 22.27 km per hour. 96% of the speeds estimated by the system of Lucivons et al. Are within a narrow range between minus 3 to and 2 km per hour. The zero range is considered ideal by traffic regulators in several countries. Without any measurement on the road, and with a synthetic dataset, our proposed system reached 85.4% of vehicles in this range. Lucivon et al. Found difficulties in measuring the speed of motorcycles to generate the ground truth. This was also a challenge in our work. We obtained an average error in the speed measurement of motorcycles of minus 80.36 km per hour with only 18.64% of the estimated speeds within the ideal error range. The rest of the measurements of the other categories of vehicles, trucks, bus, and car obtained rates ranging from 81.6% to 88.2% of estimated speeds within the ideal error range. The lowest rate is for truck and the highest is for bus. We achieved competitive results in comparison with the state-of-the-art, which performs camera calibration and makes use of a real-world dataset. Our approach can be generalized for any other scenario since we can generate customized synthetic datasets with other specific camera viewpoints. As future work, we intended to increase the number of synthetic data samples, including more scenarios and weather conditions, conducted training by using samples from other dense optical flow extraction methods, and train with other deep learning architectures. Also, the goal is to train samples by speed and types of vehicles to carry out specific training for the types of vehicles whose estimation error was high, such as motorcycles. Finally, we intended to capture samples from real-world scenario and evaluate our method on them. That's the reference that you use in the presentation. And thanks for the attention.